All right, let's get started with today's e-learning series. We're going to be talking about one-way FSI analysis with ANSYS CFD and mechanical. So starting with the presentation, FSI options in Workbench. We're looking at the one-way FSI, which means you can transfer fluid load either from ANSYS Fluent, CFX, or IcePack to mechanical systems. This does not require any external software or scripts, to couple these elements in Workbench. And geometry is shared in between CFD and the mechanical systems, so it's really convenient. And there are a couple of reasons we want to do this, and we'll see as the presentation goes along, and why are the reasons that we want to transfer the fluid load into mechanical system. In addition to one-way FSI, and of course there's a fully coupled two-way FSI. This is the data transfer at every time step between CFX and mechanical system, CFD and mechanical system. So for ANSYS CFD, both Fluent and CFX can be used in coupling with mechanical for two-way FSI calculation, and it's fully integrated, seamless load transfer with the data mapping, between the selected surface pairs in the CFD model and mechanical systems. So it does not require any additional software or external software or scripts to make this happen. So come back to the one-way FSI coupling scheme. Why are we interested in doing this? Because in many situations, we do not require a two-way FSI coupling. It's rather complex, and it requires a lot of CPU time and to get the coupling two-way FSI, fully coupled FSI analysis done. And it requires data transfer at every time step until they converge, both on the CFD side as well as on mechanical side. So prior to do that, if your system has more weak coupling, not a strong coupling, two-way FSI coupling, you can perform a one-way FSI to see the fluid load, carry over to mechanical to calculate deformation or thermal stress. We can transfer the surface pressure to static structure analysis, or surface temperature, or heat transfer coefficient, or volumetric temperature to ANSYS thermal and mechanical to do thermal stress analysis. So to look at the coupling scheme in Workbench, we started with the CFD analysis in today's demo, and then transfer the data, the solution, to a static structure to look at the deformation of from mechanical solution. And the data on the geometry can be shared, between the components. So what we're looking at in a simple example is like this. I have like a pitot tube device, suspended in free stream air. So you can see my cursor here. There's an internal flow passage where the flow is going to enter that through a narrow passage, and also a flow around this pitot tube on the external surfaces. So that would be the geometry. The highlighted part is the solid part of the tube, of the pitot tube, and the semi-cylinder is the external flow volume. So in this case, the geometry has two parts, with the solid part and the flow volume, which is external space of the probe, and the internal flow passage of the pitot tube. Right? First, we'll look at the solution and setup on the CFD side. And at this point, I'll take you through the setup of the CFD section quickly, and before we go to mechanical to do the one-way FSI coupling. So right now, if we look at the geometry, right, we have two parts. This is the solid portion of the analysis. That would be the probe, and that would be the flow volume. As you can see that is the external flow volume and this internal flow passage, inside of the probe. And because of the symmetric nature of the geometry, we can take that advantage and just use half a symmetry and calculate 1/2 of the domain, and this will be a symmetry surface. So it's a very simple geometry with the probe, with the solid part, and the flow domain. In terms of meshing for the CFD part, and I've done this, quickly and previously, so we don't waste time opening and closing these programs right here. Since we have two parts, for the fluids meshing, here we don't need the solid volume, so we suppress the solid volume. All the meshing is done here in addition to the default option is I inserted volume sizing for the entire flow domain, and of course I use the default inflation option right here. Okay, I generate the inflation layer anywhere on the solid surfaces external to the probe and in the internal flow passages, right? So with this setting, very simple setting, I have a total of roughly 92,000 elements in this configuration. And in addition to the mesh elements, I created a few boundary surfaces which I will assign boundary conditions in the CFD analysis. N represents where the flow enters the flow domain, and out, of course, leaving the domain. And I have the cylinder, which represents the ambient boundary condition, and symmetry surface, and represent the half symmetry condition. The probe itself, that would be the tube-like surface of the probe, and the stem, which I call that a support. That would be the part connecting the probe to a fixed location. So I just provided the name selections, so I can define boundary conditions in the CFD setup. So in this case, once the meshing component is completed, we'll take that into a CFX pre. In this case, we use the CFX as the CFD code, and I walk you through the quick setup of in this case. In default domain is air at the low speed, okay, and we pick the caps along the default turbulence model in this setup. So in addition to selecting the working fluid and the governing equations, we set up boundary conditions where the flow comes in on this surface. That's where we assign the inlet boundary, comes in at the variable called VIN, which will provide an expression which we can change that in the parametric setup in Workbench project page. In this case, right now, is 20 meters per second. So I have roughly a 20 meters per second wind coming at the probe, which this case roughly is about 40, 50 miles per hour wind, a pretty strong wind already in this case, okay? And in a similar manner, I set up the outflow boundary condition and the ambient condition. That would be the cylindrical surface of the external flow domain, which I'll just assume is an opening flow, is free to go in and out on these surfaces. And then I have two solid surfaces, right, boundary conditions. One is the probe itself, okay? That is the cylindrical-like surface of the probe and the internal flow passage wall, right? Two parts constitutes the surface. It's a wall. And I have the support, which is the stem that holds the probe, to a fixed point. And I have these as boundary conditions as well. So by setting up this case, I have the name selection assigned, inflow, outflow, boundary condition assigned. I'm ready to run the analysis. In the meantime, I can set up some output parameters. For example, I can monitor the force in X direction, in Y direction, in Z direction. Those would be the fluid force acting on the probe, the cylindrical probe itself, and so forth. I mean, you can see that as the calculation goes on. So once the setup is done, and we can look at the solution. And in this case, the solution is done very quickly, converges in less than 30 iterations. In 28 iterations, only takes about 30 seconds, less than a minute, for the solution to complete. And you can see here, these are the residual, and I have the user point the 3/4 component, okay? I have the 3/4 component, Fx, Fy, and Fz. That's the fluid force acting on the probe surfaces. So at this point, the calculation is complete, and we can look at the flow results. In CFD post, I can look at the surface pressure of the probe. That would be the pressure contour on the probe surfaces, on the support, and on the symmetry surface. What you see here is the incoming flow impinges on the front face of the support and these front face, the circular face of the probe. So we have a higher pressure on these locations. But then as the flow turns and accelerates through the curved surfaces immediately behind the front surface, and the pressure drops. And you could see the flow direction and so forth in the velocity vector plot. So these are the indications, flows coming from free stream, this as the velocity vector on the symmetry surface, and turns the corner, and part of it goes into the internal flow passages, and this part, hitting the front face of the support stem, okay, as well. So these are the flow solution. As the output parameter, you could see the, I defined the probe force acting on the probe. I can use that as a workbench parameter, and later as the parameter to optimize the design in the design optimization or design iteration analysis, right? You can set this up easily. So at this point, my fluid solution is complete. I have a fluid loading on the probe surfaces and the probe support. Then I'm going to see, this fluid force, how is that going to be acting on the surfaces transformed to the structure solution to provide me with a deformation and stress and so forth, okay? So at this point, if we return to Workbench, okay, we turn to Workbench project page, okay? And the CFX section is complete. If we recall quickly our coupling scheme, we need to create a static structural system for mechanical solutions, right? And later, once that is done, we need to start transfer the fluid load, import these loads, and then eventually calculate the deformation. Now we turn to the Workbench project page, just drag and drop a static structural into the project page, create that system. Okay, and now I'm going to share this geometry. The static structural is going to use the geometry that you've seen previously, and in addition to that, I'm going to transfer the solution from the CFD side to the structure side. Okay, now I'm going to look at the setup of the static structural in mechanical system. Okay. First, you notice is I do have the two parts, the flow, both the flow domain and the solid domain present in here because it's an FSI analysis. I have both parts in design modeler, and they carry it over. So for static structural, I don't need a flow volume. I can simply just suppress that part and just leave the solid volume right here, okay? And I will have to first create a mesh. I'm going to insert a sizing, just create a volume sizing for this, the entire solid part, as you point to millimeter, and look at the mesh. If I go with default mesh, there are some parts with very large elements, and may not be suitable for this analysis, okay? So I have a computational mesh right here, right? The next thing I want to do is provide the boundary condition for the structural analysis, right? So on the symmetry surface, I'm going to insert a frictionless support, okay, as a boundary condition. And on the top surface right here, I'm going to insert a fixed support. That point is fixed in space, right? So I will look at the deformation as the wind pushes the probe from the front face and so forth, right? And I have two boundary conditions set up for the structural calculation. Now you notice on the steady structure scheme right here, I have an import load, which means in this case I have fluid solution ready, or right here. All I need to do is right-click and say Insert Pressure. And where does this pressure come from? And at this point, you can see Workbench is taking the CFD solution from the CFX results and then make it available. Now I'm going to pick the probe surface, okay, as the FSI coupling surface, which means I'm going to transfer fluid pressure from CFD solution to mechanical, right? And I select the matching surface right here, right, from the CFD boundary condition. That is the reason why we need to define these surfaces, provide name selections for these surfaces in CFD analysis to make sure I can pick the corresponding boundary condition or fluid load from the CFD side, and I use that to transfer to mechanical system. After that is done, all I need to do is just click Import Load, okay? And now Workbench going through the internal mapping process to calculate pressure distribution, from the CFD side to mechanical side. And again, this is not a constant load, because CFD has a surface pressure distribution. As you can see here, indicates the magnitude and of the pressure load on the pore surface, external surface, and the internal flow passage. Okay, if I expand this item right here, okay, I can see a quick summary of how these sides are matched up. And first, you will notice that 100% of the mechanical nodes were mapped to the CFD surface, which means this is a good situation. There's no node, left hanging, and not able to find a matching component from a CFD solution. So I do have pressure load nicely mapped onto the structure part. And then you do see the force and load summary in 3 components, X, Y, Z components, okay, for the pore surfaces. So in transferring load, I'm not limited to just transferring one surface. I can have multiple load import. In addition to the probe surface, I have another component I like to transfer load in here. I insert another load transfer, and this time is the support, right? The probe support these 3 surfaces, okay? And I'm going to pick from the CFD boundary equal support. That is the boundary condition and name selection we created for the CFD analysis. And in a very similar way, I right-click, press Import Load, and Workbench, again, performing all the mapping calculation and importing CFD load from CFX solution to mechanical. And you will see a similar summary presented right here, the loads from the CFX side, XYZ components, mapped to mechanical side, XYZ component, and 100% of the nodes were successfully mapped to the CFD surface. Right? So right now, we're ready. I mean, you can look at the load transfer from the CFD solution to mechanical. And we have the boundary condition set up for frictionless support and the fixed support for the probe, and we're ready to solve. I'm going to insert a total deformation, okay, and as the quantity to look at, and solve the total deformation as a result of the fluid load acting on the probe surfaces, right? In less than a minute, I have the solution available, okay? So I can look at the total deformation. The fluid is pushing the probe, bending backwards a bit because of the free stream velocity and the pressure loads acting on the probe surfaces. Okay? So that is the procedure of coupling the fluid solution to the mechanical system. If we return to the Workbench project page, this is like what we're seeing on the PowerPoint, and I completed a fluid solution, and then use the solution, map the fluid load to mechanical part, okay, and provide the load transfer. Is there any questions at this point? Okay, no. So, in quick summary, so why are we interested in the fluids load transfer and in coupled one-way FSI situation? One of the most simplistic reason is the fluids load is usually not a constant, okay, on the surface. I mean, in mechanical, when you specify a pressure load, I mean, you can specify a constant. That would be the straightforward way. But very often, loads come from fluids, is a contour. We have surface pressure contour. And the constant load assumption is probably not a great idea when there's a large pressure gradient exists, right? So you have a pretty large load differential from one point on the surface to the next spot on the surface, which the deformation you calculated in the mechanical system is going to be greatly different from that situation. So in case the fluid load is substantial, and so you want to consider importing a fluid load, this is a great way to start, okay? And to consider one-way FSI, because one-way FSI provides, the advantage, for example, like load transfer from CFD to mechanical, and we've seen that the automatic mapping and load import procedure. We only need to identify the mapped surface pairs, one from the fluid side and the other one from the mechanical side, right? And this procedure is not limited to just one surface. You can import as many surfaces as you want, as long as you have the pair identified, from both sides, from the CFD side, the structure side as well. And this procedure works for transient load any time step as well. So, for example, if you have a transient analysis, you have time step 1 to 10. I can use this one-way FSI procedure to transfer fluid load from time step 1, if I'm interested to see the deformation on that part, or from time step 3 or time step 5, to the mechanical system, right? And you are now limited to just look at the steady state coupling process, and you can get load transfer from the transient analysis as well. And the other useful, very useful advantage for one-way FSI is, we can identify model validity, and the multi-field coupling physics, right, from the fluid side to the solid side. We can investigate if the coupling is substantial, if it's a strong coupling or it's a weak coupling between the two systems. By going through this process very quickly and check the model, if the model, both the CFD model and the mechanical model work correctly, okay, corresponding to the load transfer and by themselves, work independently by themselves, right? And we can identify this, throughout this process. And then, as a conclusion to this is like we can use that as a prelude to a potential two-way FSI analysis. If the coupling proven, is very strong between the two components, for example, fluid loads, lead to a large deformation on the structure side, and because of the large deformation, that creates a new boundary surface for the fluid solution. And we need to take that into account, the boundary deformation. And that obviously creates a new fluid solution for the next time step or next coupling step situation, and that forms a strong 2FSI analysis. By performing the one-way analysis, we can identify seeing the structural response is strong or it's not that great, and do we need to go to the two-way FSI analysis, okay? And is it necessary to perform a full coupled 2FSI analysis? And these present you a great set of tools using ANSYS Workbench, ANSYS CFX, either CFX, Fluent, or IcePack, and get fluid load, pressure load, surface pressure, or surface temperature or heat transfer coefficient to ANSYS Mechanical, provide the coupling between these components.